spherical coordinates. Spherical coordinates are going to spring from cylindrical coordinates in this way. So suppose that you have the cylindrical coordinates and the cylindrical coordinate formulas. The thing that we're going to try to get is the formulas for spherical coordinates. And the way that we're going to do it is like this. First of all, what are going to be the numbers describing the point? Now, the first number is going to be the distance from the origin to the point. That's called rho. In particular, notice that rho squared is going to be equal to x squared plus y squared plus z squared, just because it's going to give you the distance to the point. Phi is the angle between the positive z-axis and the line segment from the origin to the point. So you take this line segment and you take the angle that makes with the positive z-axis, and that's going to be phi. So we have rho and phi. And the other one is going to be theta, that we already know. In spherical coordinates, we are going to describe a point by rho, theta, and phi, more or less the same way that we did with polar and cylindrical coordinates. Now, by trigonometry, we know that r is going to be equal to rho sine of phi, just trigonometry, and the other one, the other side of this right triangle, it's going to be given by rho cosine of phi. Notice that in this particular case, well, in this triangle, this is also the angle phi. So, plugging into cylindrical coordinates, we have this expression right here, and that's are going to be, or these expressions, and those are going to be the spherical coordinate formulas. So notice that it's not very difficult to see. This is r cosine of theta, this is r sine of theta, and this is z. So it's just taking cylindrical coordinates and doing some trigonometry to get that. The volume of a spherical wedge can be approximated by these, where the first one is the area of the polar rectangle, and the second one is just going to be an approximation of the height. Well, if you multiply two, well, first of all, I can expand this r. This r was obtained from the formula for polar rectangles, and then we are going to obtain rho sine of phi k. And let me just call it phi star at this moment. And the thing that we're going to say is the volume of spherical wedge is not equal, but I mean, I'm saying here, but that is equal, but it can be approximated by this. Or if we pick a particular point, we can get that the volume is equal to that. And you can prove that. It's not of my main interest to explain you that. The only thing that I wanted to do with this expression is try to more or less give you an idea of where this particular rho square sine of phi comes from. Why? Because that's going to be by using the Riemann sums and the limit of the Riemann sums. That's exactly what is going to be needed, or you need to remember when you're changing to spherical coordinates. So it's going to be rho square sine of phi. Now notice that this is in a spherical wedge. In other words, the thing that we're saying is a spherical wedge is a particular solid that such that the rho goes from a number to a number, the theta goes from a number to a number, and the phi goes from a number to a number. Let me give you an example. So a unit ball is actually a spherical wedge. Why? Because if you have the unit ball over here, we can check that in spherical coordinates rho moves from 0 to 1. In this case, rho moves from 0 to 1. Theta moves from 0 to 2 pi because it goes all the way around. And now notice that the phi actually moves only from 0 to pi because since the theta went all the way around, phi only has to cover half of the maximal semicircle. So now the only thing that we do is we grab our function and we just plug in the values for each one of our variables. So in this case, we have our function, change everything into spherical coordinates, so x squared plus y squared plus z squared is equal to rho squared, and then we add this rho squared sine of phi, and then we integrate d rho, d theta, d phi. We compute the integral, so it's going to eventually give you this result that I have on the bottom. But the most important thing that I want you to notice is how to set up this particular integral. One other thing that I want you to check out is triple integrals with spherical coordinates once your region is not a spherical wedge. So suppose now that you have that theta moves between a number and a number, phi moves between two functions that depend on theta, and a row moves between two functions that depend on phi and theta. And this is usually the case for these particular regions. So the thing that we're going to do is we're going to do more or less the same. We're going to keep rho square sine of phi, change your function to spherical coordinates, and then integrate first with the function that the variable, in this case rho, that moves between the function of the other two. So in this case rho moves between those two functions. Then you do phi that moves between two functions that depend on theta, and then theta that moves between two numbers. Again, I don't suggest you to remember this formula just like that. The only thing you really need to remember is the rho square sine of phi and how to change everything to spherical coordinates. Now the setup comes a little bit easier once you have your region. So let me just give you an example. This is the volume of the solid region above the cone and below that particular sphere. So the sphere centered at 0, 0, 1/2, or radius 1/2, is denoted like this, and this is the regular rectangular coordinate equation that if we simplify, you obtain this. Why I want it in this form? Because I know that x squared plus y squared plus z squared is equal to rho squared. Now I'm going to do the same for the cone. The cone is given by this, and the equation is right here. Now the first thing that I'm going to do is I'm going to change everything into spherical coordinates. So, well, this is your solid, and now let's start. We change the equation to spherical coordinates, so the equation of the sphere is equal to, so you have rho squared here equal to c, but remember c is rho cosine of phi. So in other words, once I divide by rho, the thing that I have is rho is equal to cosine of phi. And the equation of the cone is phi equal to pi over 4. Notice that all these points are, when you draw a line segment to the origin, are on an angle of pi over 4 with the positive z-axis. So now that we have that the region E can be described by, and the only thing that I want you right now to identify is that this pi over 4 is going to be the limit of the phi, and this rho equal to cosine of phi is going to be the limit of the rho. Let me just give you a little bit more in-depth explanation. The theta is going to move from 0 to 2 pi, so you're going to go all the way around. The phi is going to move from 0 to pi over 4, so it's going to start here and it's going to angle up to pi over 4 with respect to the positive z-axis. And the rho is going to go from 0 up to the sphere, but the sphere, remember, is cosine of phi. So now we just set up the integrals, and the volume is going to be the triple integral over E dv. And then once you change the spherical coordinates, you have to add the rho square sine of phi. And then you just keep your variables right away. Now notice that rho moves from cosine of phi to 0, so the rho is the first one that we're going to integrate with respect to, and the other two, since they are moving between numbers, you can use whichever order you want for those two. And this is the solution. You can check in detail my work later on, or by pausing this particular video.